Look up at the night sky and you'll see countless stars shimmering like distant lanterns. But have you ever wondered where they come from? Hidden in the darkest corners of space, vast clouds of dust and gas drift silently, invisible to the naked eye. These cosmic shadows aren't just empty voids, they're bustling stellar nurseries, the secret cradles where stars are born. And within their swirling depths lies the answer to one of the universe's greatest mysteries: how the dazzling lights above us came to be. Picture this, a single dust cloud stretching light years across, so dense that not even light can escape its grasp. Yet inside this seemingly lifeless darkness, gravity works its magic, pulling particles together until the pressure ignites a fiery spark. That spark grows into a star, and suddenly the darkness gives way to light. It's a process that's been happening for billions of years, shaping galaxies and filling the cosmos with the very elements that make life possible. But how do we uncover the secrets of these cosmic nurseries when they're hidden behind walls of dust? The answer lies in the clever tricks astronomers use to peer through the shadows, revealing the extraordinary drama unfolding inside. This isn't just a story about distant stars, it's a story about us. Every atom in your body, every breath you take, was forged in the heart of a star born in one of these stellar nurseries. By understanding how these cosmic cradles work, we're piecing together our own origins, tracing the journey from stardust to human life. So buckle up, because today, we're diving deep into the heart of these enigmatic dust clouds. We'll uncover how they birth stars, why they hold the key to the universe's evolution, and how scientists are unraveling their mysteries one discovery at a time. The journey begins now. Let's step into the shadows and witness the birth of light itself. These cosmic dust clouds are far from simple blankets of darkness. They're dynamic, chaotic realms where the universe's most fundamental forces collide. Imagine a sprawling metropolis, but instead of buildings and streets, it's a tangled web of gas molecules and microscopic dust grains, each particle drifting in the frigid void. Some of these clouds stretch hundreds of light years across, containing enough material to forge thousands of stars like our sun. Yet despite their staggering size, they remain ghostly and elusive, visible only when silhouetted against brighter cosmic backdrops or when infrared telescopes pierce their veil. What makes these clouds so special isn't just their size, it's their recipe. They're mostly hydrogen, the universe's simplest and most abundant element, mixed with traces of helium and dust grains finer than smoke particles. But sprinkled within are tiny amounts of carbon, oxygen, and silicon, the raw ingredients for planets and life itself. When temperatures inside these clouds plummet to just 10 degrees above absolute zero, something remarkable happens. Atoms slow down, molecules form, and the gas becomes sticky, clinging together in fragile structures. This is where gravity takes over, amplifying tiny clumps into dense knots. Yet gravity doesn't work alone. Turbulence, the same chaotic force that stirs storm clouds on Earth, whirls through these cosmic nurseries, creating pockets of higher density. Think of it like cream swirling in coffee. Some regions bunch together while others stretch thin. Over millions of years, the densest knots grow heavier, pulling in more material until their cores collapse under unimaginable pressure. That's the moment a star is born, a spark flaring to life in the darkness. But here's the twist. Without dust, none of this would happen. Those microscopic grains act like cosmic refrigerators, radiating heat away and allowing the gas to cool and condense. They also provide surfaces where molecules can assemble, like a microscopic construction site for the universe's building blocks. Astronomers call these clouds molecular for a reason. They're the only places cold and dense enough for molecules to survive. In the harsh radiation of space, most molecules get torn apart, but inside these dusty sanctuaries, they thrive. Water, carbon monoxide, even complex organic molecules like alcohol and sugar have been detected within them. It's as if the universe is prepping a chemistry set, gathering the materials needed not just for stars, but for the planets and life that might follow. So when we study these cosmic shadows, we're not just witnessing star birth. We're uncovering the hidden workshop where the ingredients of everything, including us, are patiently assembled. The birth of a star isn't some gentle cosmic whisper. It's a full-blown celestial showdown where gravity, turbulence, and radiation battle for dominance. Picture a swirling dust cloud as a vast, chaotic dance floor where particles collide and cling together in a slow, relentless waltz. At first, these clumps are no bigger than grains of sand, but gravity keeps pulling, drawing them closer, packing them. As the density increases, so does the heat, until the core becomes a seething pressurized furnace. When temperatures soar past 10 million degrees, hydrogen atoms finally surrender, fusing into helium in a flash of nuclear fire. That's the moment a star flickers to life, transforming a cold, dark pocket of space into a radiant beacon. But here's the mystery. Not every clump becomes a star. Some fizzle out, torn apart by competing forces before they ever ignite. Magnetic fields weave through these clouds like invisible threads, sometimes holding gas together, other times whipping it apart. Radiation from nearby stars can blast through like a cosmic sandblaster, eroding fledgling stellar embryos before they've had a chance to grow. Even turbulence plays a role. Think of it as the universe's way of stirring the pot, creating pockets of opportunity where stars can form while leaving other regions barren. It's a delicate balance, where the slightest shift can mean the difference between a dazzling newborn star and a silent, drifting cloud. And the stars that do emerge, they're not all the same. Some are colossal, burning bright and fast, destined to explode in spectacular supernovae after just a few million years. Others are modest, like our sun, settling into a steady glow that lasts for billions of years. The difference often comes down to the initial conditions, how much material was available, how quickly it collapsed, and whether competing forces gave it room to breathe. It's a cosmic lottery, where the prizes range from faint red dwarfs to brilliant blue giants. Yet even after ignition, the drama isn't over. Young stars often unleash furious winds, blasting away the remaining gas and dust that once shrouded them. These stellar tantrums can trigger new waves of star formation nearby or snuff out neighboring nurseries before they've had their chance. It's a reminder that star birth isn't just a single event, it's a chain reaction, a sprawling saga where every ignition sends ripples through the cosmos. And hidden within these ripples are clues to how galaxies evolve, how planets assemble, and ultimately how life finds a way. Among these cosmic cradles, the Orion Nebula stands out like a beacon, a stellar nursery so vivid that even backyard telescopes can spot its glowing gases from over 1,300 light-years away. What we're seeing is essentially a maternity ward for stars, where newborn suns flicker to life amidst swirling veils of pink and gold. But Orion isn't just pretty, it's a laboratory for understanding how stars form. Inside its turbulent heart, protostars, stellar infants still wrapped in their dusty cocoons, siphon gas from their surroundings, growing hotter and denser until nuclear fusion kicks in. Meanwhile, massive young stars, some dozens of times heavier than our sun, blast the nebula with ultraviolet radiation, sculpting the gas into intricate pillars and cavities. It's a place of creation and destruction, where the very act of star birth reshapes the nursery itself. What sets stellar nurseries apart from ordinary dust clouds is their sheer dynamism. Think of them as cosmic construction sites, where gravity's slow pull battles against the chaos of magnetic fields and stellar winds. In the Orion Nebula, for example, astronomers have spotted disks of gas and dust swirling around baby stars, some of which will eventually coalesce into planets. These disks are like cosmic pottery wheels, where the raw material for future solar systems takes shape. But the environment is far from serene. Radiation from nearby massive stars can strip away these disks in just a few million years, a reminder that star formation is a race against time. Only the fastest-growing protostars survive to adulthood, while others see their potential planetary systems vaporized before they've even formed. Yet nurseries like Orion aren't just factories for stars, they're also recycling centers. When massive stars die in supernova explosions, they spew heavy elements like iron and silicon back into the surrounding cloud. These enriched materials become the building blocks for the next generation of stars and planets. It's a self-sustaining cycle. Stars are born, they live, they die, and their remains fuel new beginnings. This means the carbon in your bones, the oxygen in your lungs, even the gold in your jewelry. All of it was forged in stellar nurseries like Orion, then scattered across space by dying stars. The more we study these nurseries, the more we realize how deeply personal they are. Every star, every planet, every ingredient for life traces back to these swirling clouds of dust and gas. And while Orion might be the most famous, it's far from alone. From the towering pillars of the Eagle Nebula to the fiery chaos of the Carina Nebula, stellar nurseries come in countless shapes and sizes, each with its own story to tell. They're proof that even in the darkest corners of space, light always finds a way to break through. Gravity is the silent architect of the cosmos, the unseen hand that transforms drifting dust into blazing stars. Picture it as a cosmic sculptor, patiently gathering scattered gas and dust, pulling them closer with an unrelenting embrace. At first, the process is achingly slow, a single particle drifting toward another over thousands of years. But as more material accumulates, gravity's grip tightens, compressing these fragile clouds into dense, swirling knots. Each knot becomes a stellar womb, a place where pressure and heat build until the conditions are just right for nuclear fusion to ignite. Yet gravity's work is far from simple. It doesn't operate in isolation, it's locked in a constant tug-of-war with other cosmic forces. Turbulence, the same chaotic energy that churns storm clouds on Earth, whips through these stellar nurseries, creating pockets of resistance. Magnetic fields thread through the dust like invisible wires, sometimes propping up collapsing gas, other times channeling it away. It's a delicate balancing act. Too much turbulence and the cloud shatters, too strong a magnetic field and the gas can't collapse at all. Only when gravity overcomes these rivals does a star truly begin to form. The strength of gravity's pull also dictates what kind of star emerges. In regions where matter piles up densely, gravity works overtime, forging massive stars that burn hot and fast. These celestial giants live spectacular but short lives, ending in fiery supernovae that seed the cosmos with heavy elements. In quieter corners where material is sparser, gravity crafts smaller, steadier stars like our sun, patient sustainers that glow for billions of years. The difference between a brilliant blue giant and a modest red dwarf often comes down to how much material gravity could gather before fusion began. But here's the twist. Gravity isn't just a creator, it's also a destroyer. As young stars ignite, their intense radiation and stellar winds push back against the very forces that birthed them, carving cavities in the surrounding cloud. This feedback can stifle further star formation nearby, or paradoxically, trigger new collapses by compressing neighboring gas. It's a cosmic dance of creation and resistance, where every newborn star alters the conditions for the next. And hidden within this dance are clues to how galaxies evolve, how planets assemble, and ultimately how the universe builds the ingredients for life itself. Turbulence is in the cosmic game of star formation, a force as unpredictable as a hurricane tearing through a quiet town. While gravity methodically pulls matter inward, turbulence whips through dust clouds like an invisible mixer, churning gas into swirling eddies and violent shockwaves. This chaos isn't just background noise, it's a decisive player in whether a cloud births stars in a slow trickle or a sudden explosion of light. Picture a pot of water on the boil. Some bubbles rise gently, while others erupt violently. Stellar nurseries operate the same way, with turbulence dictating the tempo of creation. In some regions, turbulence acts as a cosmic brake, preventing gas from collapsing too quickly under gravity's pull. This slower collapse allows smaller, more stable stars like our Sun to form, giving them time to gather just enough material without growing unruly. It's like building a house brick by brick instead of dumping all the materials at once. The structure holds together better. But elsewhere, turbulence does the opposite, slamming gas pockets together with such force that it sparks rapid star formation. These shockwaves can trigger chain reactions, turning quiet corners of a cloud into stellar fireworks displays where dozens of stars ignite almost simultaneously. The balance between these two outcomes hinges on the cloud's internal drama. Magnetic fields, like invisible scaffolding, can channel turbulence into organized flows, while radiation from nearby stars might amplify the chaos. Astronomers have even spotted turbulent cores, dense knots of gas where turbulence and gravity are locked in a tug-of-war, each vying to dictate the next chapter of star birth. It's a reminder that the universe thrives on contrast. Without turbulence's chaos to counter gravity's order, we might only have massive stars flaring briefly before vanishing, leaving no time for planets or life to take root. What makes turbulence especially fascinating is its fingerprints on entire galaxies. In sprawling nebulas like the tarantula, turbulence whips gas into frenzied spirals, creating pockets where stars form in frantic bursts. In quieter clouds like those in the Taurus constellation, gentler motions allow for solitary, steady star formation. This duality explains why some galaxies blaze with young stars while others glow with the steady light of ancient suns. Turbulence, it turns out, isn't just a local phenomenon. It's a cosmic rhythm, one that shapes the character of the universe itself. Deep within these stellar nurseries, an invisible alchemy unfolds, one that turns sparse atoms into the building blocks of stars. Hydrogen, the universe's simplest and most abundant element, drifts through these clouds like solitary wanderers, while helium lingers as a silent companion. But it's the trace ingredients, carbon, oxygen, even microscopic grains of silicon, that transform this cosmic soup into something extraordinary. When temperatures plummet to near absolute zero, something magical happens. These atoms begin to stick together, forming molecules as delicate as frost on a winter window. Carbon monoxide, water ice, and even complex organic compounds like methanol emerge, clinging to dust grains like tiny chemical beacons. These molecules aren't just passive spectators, they're active players in star birth. Think of them as nature's cooling system. As gas collapses under gravity's pull, it heats up, and without a way to shed that heat, the cloud would simply rebound, scattering like a spring uncoiling. But molecules like carbon monoxide step in, radiating energy away into space, allowing the gas to cool and condense further. It's like opening a window in a stuffy room. The molecules let the heat escape, making it easier for gravity to pull everything inward. Without this refrigeration effect, stars might never form at all, or they'd ignite so violently that stable solar systems like ours would be rare. The dust grains themselves are unsung heroes. Though smaller than a wavelength of light, they provide surfaces where molecules can assemble, like microscopic dance floors for atomic partners. Some of these grains are coated in icy mantles, where chemical reactions brew complex compounds, ammonia, formaldehyde, even the precursors to amino acids. It's a cosmic kitchen where the ingredients for planets and life are quietly prepared long before stars begin to shine. But here's the twist. The chemistry changes as the cloud evolves. Near newborn stars, radiation tears molecules apart, leaving behind hardy survivors like molecular hydrogen. In colder, darker regions, exotic ices and compounds thrive. This dynamic interplay means no two stellar nurseries are chemically identical. The Orion Nebula, for example, is rich in sulfur and oxygen compounds, while the Taurus molecular cloud harbors vast reservoirs of frozen carbon monoxide. These differences shape the kinds of stars and planets that emerge, painting the universe with a breathtaking diversity of worlds. What's truly humbling is realizing that the air in your lungs, the water in your glass, and the iron in your blood all began in these molecular clouds. Every heavy element was forged in stellar furnaces, then scattered by supernovae to enrich new generations of star-forming gas. The chemistry that birthed our sun and our planet is still at work today in distant nebulae where future solar systems stir to life. So when we study these cosmic ingredient lists, we're not just decoding star formation. We're reading the recipe for existence itself. Starlight isn't the only way to see the universe. Sometimes you have to feel the heat. Thick dust clouds might block visible light, but they're no match for infrared radiation, the faint thermal glow of cosmic objects. This is where astronomy's stealth mode kicks in. Telescopes like the James Space Telescope don't just observe the night sky. They detect warmth, picking up the subtle heat signatures of stars still hidden in their dusty wombs. Imagine trying to find a lit match inside a smoke-filled room. Visible light gets swallowed, but the heat, that's unmistakable. Infrared astronomy lets us do exactly that, piercing through obscuring veils to witness star birth in real time. Take protostars, for example. These stellar infants are still swaddled in thick blankets of gas and dust, invisible to traditional optical telescopes. But in infrared, they glow like embers in the dark. The James Space Telescope has captured stunning images of these hidden nurseries, showing delicate filaments of gas spiraling into newborn stars, their gravity pulling material inward like cosmic whirlpools. Without infrared eyes, we'd miss these critical early stages, like trying to understand human life by only studying adults. The details matter: how fast a protostar grows, how it interacts with its surroundings, even the chemical makeup of its cradle. Infrared reveals it all, turning what was once inscrutable darkness into a vivid cosmic scrapbook. But the magic doesn't stop at detection. Infrared light also carries chemical fingerprints. Different molecules absorb and emit specific wavelengths, allowing astronomers to map the ingredients swirling around young stars. Water vapor, carbon monoxide, even complex organic molecules, all leave telltale signatures in infrared data. It's like analyzing smoke from a distant fire to figure out what's burning. These observations have revealed something astonishing. The building blocks of planets and life are already present in the chaos of star formation. The same clouds that birth stars also brew the chemistry for future worlds. Yet infrared astronomy isn't just about seeing through dust, it's about rewinding time. The most distant galaxies, whose light has been stretched into infrared by the expanding universe, appear to us as they were billions of years ago. By studying them alongside nearby stellar nurseries, we're piecing together how star formation has evolved across cosmic history. It's a humbling thought. The same tools that show us a star being born today also let us glimpse the universe's fiery infancy. And with every new infrared breakthrough, we're not just solving mysteries. We're rediscovering the universe in a light we've never seen before. Hidden deep within the swirling chaos of a stellar nursery, a protostar begins its life not with a brilliant flash, but with a slow, gravitational whisper. Imagine a tiny knot of gas and dust, no larger than our solar system, quietly pulling in more material from the surrounding cloud. At this stage, it's not yet a star, just a dense, hot core, glowing faintly with the warmth of its own contraction. But this humble beginning holds the potential to become something extraordinary, a blazing sun that could one day light up an entire planetary system. The journey from protostar to full-fledged star is a delicate balancing act. Gravity works tirelessly to pull matter inward, compressing the core until temperatures skyrocket past 10 million degrees, the threshold for nuclear fusion. But the protostar isn't just gathering mass, it's also battling to hold on to it. Violent jets of gas often erupt from its poles, shooting light years into space, while fierce stellar winds push against the infalling material. It's a cosmic tug-of-war, too much radiation, and the star scatters its own building blocks, too little accumulation, and it fizzles out into a dim, failed star known as a brown dwarf. What makes this phase so fascinating is its unpredictability. Some protostars grow rapidly, greedily devouring gas from their surroundings and igniting fusion in just a few 100,000 years, a blink of an eye in cosmic terms. Others take millions of years, inching towards stardom as they compete with siblings in the same nursery for limited resources. And then there are the ones that fall short entirely, collapsing into brown dwarfs, objects too massive to be planets but too small to sustain the fires of true stardom. These stellar almosts glow faintly with residual heat, a quiet reminder of how precarious star birth can be. But even the successful protostars face hurdles. Magnetic fields twist around them like invisible spiderwebs, channeling some material onto the star while flinging the rest away. Disks of dust and gas, future planetary systems, swirl around the newborn star, sometimes feeding it, other times fragmenting into clumps that might become planets or rival stars. It's a messy, chaotic process, one that shapes not just the star itself, but everything that might someday orbit it. The story of a protostar is more than just physics, it's a tale of cosmic potential. Every flicker of light we see in the night sky began this way. A struggle against darkness, a fight against dispersal, and ultimately a triumph of gravity over chaos. And when we peer into stellar nurseries with infrared eyes, we're not just watching distant events. We're witnessing the origins of the very elements that make our existence possible, a reminder that stardust runs through us all. Objects are the universe's way of letting off steam, spectacular jets of gas screaming across space at hundreds of kilometers per second, lit up like neon signs in the dark. These aren't just random cosmic fireworks. They're the birth cries of baby stars, violent outbursts that reveal the turbulent adolescence of stellar formation. Picture a young star, still gathering material from its dusty cocoon, spinning faster and faster as it grows. But there's a problem: it can't hold on to all that energy. Like a spinning ice skater flinging out their arms, the star needs to shed angular momentum, and it does so by launching twin jets from its poles, piercing through the surrounding cloud like cosmic blowtorches. What makes these jets so fascinating isn't just their speed, it's their structure. Some twist into elegant spirals, others knot themselves into shockwaves as they slam into slower-moving gas. Astronomers have spotted objects with multiple bow shocks, stacked like ripples in a pond, each marking a pulse of activity from the restless young star. The material in these jets isn't just random gas, either. It's packed with molecules like hydrogen and carbon monoxide, glowing fiercely as they collide with interstellar material. These collisions heat the gas to thousands of degrees, making objects some of the hottest natural phenomena in the cosmos, despite originating from some of its coldest nurseries. But why do these jets exist at all? The answer lies in the star's magnetic prison. As a protostar gathers mass, its magnetic field lines act like cosmic guide rails, channeling and fouling gas toward its poles. Some material lands on the star, but some gets whipped up and ejected at incredible speeds, like debris flung from a spinning top. This process isn't just a side effect, it's crucial for the star's survival. Without these jets, a young star would spin itself apart, tearing its own structure apart before fusion could stabilize it. The jets act as a release valve, balancing the star's growth against its own destructive forces. Studying objects is like reading a stellar diary. They tell us how stars manage their violent youth. Some jets last just a few thousand years, flickering out as the star settles into adulthood. Others persist for much longer, sculpting their surroundings into intricate shapes that linger for. The famous object HH-34, for example, looks like a celestial firework frozen in mid-explosion, its delicate arcs tracing the star's tantrums across light-years of space. Each of these structures holds clues about the star's mass, rotation, even the magnetic fields that shaped its birth. Perhaps the most astonishing thing about these jets is their reach. They don't just fade quietly into the void, they plow through their parent clouds, compressing gas and triggering new waves of star formation. It's a breathtaking feedback loop. Stars create jets, jets create shockwaves, and shockwaves birth new stars. This means objects aren't just byproducts of stellar formation. They're active participants in the life cycle of galaxies, weaving the threads of creation and destruction into the fabric of the cosmos. So the next time you gaze at a distant nebula, remember, hidden in its folds might be a newborn star, painting the darkness with jets of radiant gas, writing its story across the sky. In the chaotic dance of stellar nurseries, not every collapsing gas cloud gets to wear the crown of a true star. Some linger in cosmic limbo, too massive to be planets, yet too feeble to ignite the fires of nuclear fusion. These are brown dwarfs, the universe's enigmatic inn, and their very existence forces us to rethink the boundaries of what makes a star a star. Imagine an object with dozens of times the mass of Jupiter, glowing faintly with the leftover heat of its birth, but lacking the heft to fuse hydrogen in its core. It's neither fully star nor fully planet, but something altogether different, a celestial misfit that defies easy classification. What makes brown dwarfs so fascinating isn't just what they lack, but what they reveal. Born from the same dense pockets of gas as stars, they follow the same initial script. Gravity pulls, the cloud contracts, and temperatures rise. But somewhere along the way, the process stalls. Maybe the protostar doesn't gather enough mass, or perhaps turbulence and magnetic fields disrupt its growth. The result is an object that flickers briefly with deuterium fusion, a weaker cousin to hydrogen fusion, before settling into a slow, prolonged cooling. Over billions of years, its faint glow dims until it becomes little more than a shadow against the cosmic backdrop. Yet brown dwarfs aren't just stellar failures, they're laboratories for extreme physics. Their atmospheres, for instance, are wild frontiers where clouds of molten iron and sand swirl in turbulent skies. Some even show weather patterns with violent storms raging across their surfaces. And then there's their peculiar habit of floating alone in space, untethered to any star. While most planets orbit a parent sun, brown dwarfs often wander the galaxy solo, like cosmic nomads. This independence raises a tantalizing question. If a brown dwarf drifts through space with its own collection of planets, does it count as a miniature star system? Or is it just an oversized planet with entourage? The discovery of brown dwarfs has also forced astronomers to sharpen their definitions. Traditionally, stars were defined by fusion, planets by orbit, and brown dwarfs, well, they slipped through the cracks. Modern classifications now hinge on mass. Below about 13 times Jupiter's mass, you're a planet. Above that, but too light for full hydrogen fusion, you're a brown dwarf. But nature, as always, delights in exceptions. Some brown dwarfs orbit stars like planets, while others form in pairs like binary stars. This blurring of lines suggests that the universe cares little for our tidy categories. It simply builds what physics allows, leaving us to make sense of the diversity. Perhaps the most surprising thing about brown dwarfs is how common they might be. Recent surveys suggest our galaxy could harbor billions of them, lurking unseen in the dark. Some could even be closer than we think, hidden neighbors in the cosmic neighborhood, too dim to spot with traditional telescopes. Their prevalence hints at an unseen population of celestial objects, quietly challenging our assumptions about how star formation works. After all, if so many collapsing clouds become brown dwarfs instead of stars, what does that say about the recipe for stellar birth? Studying these objects isn't just academic, it's a window into the extremes of planetary and stellar evolution. Brown dwarfs embody the universe's reluctance to fit into boxes, reminding us that the cosmos thrives on ambiguity. They're not failed stars or overgrown planets, but something uniquely their own, a third way, a missing link between the blazing suns and the wandering worlds. And as we uncover more of their secrets, we're not just solving a classification puzzle. We're rewriting the story of how celestial bodies come to be, one dim, mysterious glow at a time. Star clusters are the universe's family portraits, snapshots of stellar siblings born from the same swirling cradle of dust and gas. Picture a bustling cosmic kindergarten where hundreds, sometimes thousands, of stars emerge together, their gravitational bonds as strong as shared DNA. The Orion Nebula cluster is a perfect example, a glittering gathering of young stars, some still wrapped in the gauzy remnants of their birth cloud, others blazing fiercely as they carve out their place in space. These clusters aren't random assortments. They're telltale signs of a single monumental event, a giant molecular cloud collapsing under its own weight and fragmenting into multiple stellar seeds. What keeps these stellar families together? Gravity, of course, but with a twist. The denser the birth cloud, the more tightly packed the resulting cluster will be. Think of it like a crowded room. The more people you squeeze in, the harder it is to move without bumping into someone. In clusters like the Pleiades, stars are born so close that their mutual gravity locks them into a delicate dance, orbiting a common center of mass for hundreds of millions of years. But in looser clouds, where material is sparser, stars form with more breathing room. Their gravitational ties are weaker, and over time, even gentle nudges from passing gas clouds or galactic tides can send them drifting apart like dandelion seeds in the wind. The fate of a star cluster hinges on this balance between kinship and chaos. Take open clusters, for example. They're the cosmic equivalent of a tight-knit group of friends who eventually grow apart. Born with relatively low mass, their stars are just barely bound together, and over time, gravitational interactions fling them outward into the galaxy's spiral arms. The Hyades cluster, visible to the naked eye, is slowly doing this right now, its stars scattering like marbles spilled across a floor. Globular clusters, on the other hand, are the universe's enduring families. These ancient, spherical swarms contain hundreds of thousands of stars crammed into a space just a few dozen light-years across. Their sheer density makes them nearly indestructible, allowing them to survive for billions of years, outliving countless generations of their more fragile open cluster cousins. Yet even the mightiest clusters aren't immune to change. Close encounters between stars can slingshot some members outward, while others sink deeper into the cluster's core in a process called dynamical friction. Over eons, this gravitational shuffling can transform a cluster's structure, creating dazzling central hubs where stars crowd together like commuters in a cosmic train station. The interplay doesn't stop there. Massive stars, with their shorter, often die explosively, their supernovae blasting away nearby gas and further sculpting the cluster's destiny. It's a reminder that star clusters aren't static exhibits, they're dynamic ecosystems, evolving in ways that mirror the galaxies they inhabit. The legacy of these clusters stretches far beyond their glittering appearances. As they disperse, their stars become galactic travelers, carrying the chemical fingerprints of their birthplace across the Milky Way. Our own sun might have started life in a cluster like the Orion Nebula, its siblings now lost to time and distance. Finding these long-lost stellar relatives is like piecing together a cosmic ancestry. Astronomers hunt for stars with matching ages and compositions, clues hidden in the light they emit. Every cluster, whether tightly bound or long dissolved, tells a story of shared origins and inevitable change, a testament to the delicate interplay of gravity, time, and the restless nature of the universe itself. Every stellar nursery begins as a whisper in the void, a delicate wisp of gas and dust drifting through the interstellar darkness. But these clouds are far from eternal. Like on a cosmic shoreline, they're shaped and reshaped by forces both creative and destructive. There starts quietly, as gravity gently tugs stray atoms together, forming fragile structures that might one day ignite into stars. Yet even as new suns flicker to life within them, the very energy they release begins to dismantle their cradle. Radiation, fierce as a desert wind, scours away the surrounding gas, while stellar winds blast outward like invisible hurricanes. Over millions of years, what was once a dense, star-forming fortress becomes a scattered veil of molecules, its legacy written in the newborn stars it leaves behind. This dispersal isn't just an ending, it's a transformation. The material blown away by young stars doesn't vanish. It joins the interstellar medium, a vast reservoir of recycled gas and dust that will one day coalesce into new clouds. It's a cosmic recycling program on the grandest scale. Heavy elements forged in stellar cores, carbon, oxygen, iron, are flung into space, enriching future generations of stars and planets. The Orion Nebula offers a stunning glimpse of this process in action. Its massive stars, like the brilliant trapezium cluster, have carved enormous cavities in their birth cloud, their ultraviolet radiation ionizing the gas into glowing tendrils. Yet even as the nebula dissipates, pockets of denser material remain, collapsing under their own weight to form the next wave of stars. Creation and destruction exist in lockstep, each dependent on the other. The speed of a cloud's dissipation hinges on the stars it births. Gentle, low-mass stars like our Sun churn out modest stellar winds, allowing their nurseries to fade gradually over eons. But massive stars, those behemoths dozens of times heavier than the Sun, are ruthless architects of chaos. Their intense radiation strips electrons from nearby atoms, heating the gas to searing temperatures and driving it outward in explosive bubbles. Supernovae, the spectacular deaths of these giants, deliver the final blow, shockwaves rippling through the cloud and scattering its remnants across light years. The Crab Nebula, the aftermath of a supernova observed in the year 1054, shows this violence in vivid detail, filaments of gas racing outward at thousands of kilometers per second, carrying the ingredients for future stars and planets into the galactic winds. Yet amid this turbulence, there's remarkable order. The dispersal of one cloud often triggers the collapse of another. Shockwaves from dying stars compress nearby gas, seeding new pockets of star formation in a self-perpetuating cycle. In galaxies like our Milky Way, this rhythm ensures that star birth continues across billions of years, weaving an unbroken thread from the earliest epochs to the present day. The interstellar medium isn't just a graveyard for old clouds. It's a nursery in waiting, where gravity, turbulence, and time conspire to begin the process anew. What's truly humbling is realizing how deeply personal this cycle is. The oxygen we breathe, the iron in our blood, even the calcium in our bones, all were forged in stars that lived and died long before our sun ignited. Their remains became part of the molecular clouds that birthed our solar system, linking us to this endless cosmic dance. So when we gaze at a dissipating nebula, we're not just witnessing an ending. We're seeing the universe's way of turning stardust into life, one fleeting cloud at a time. When a massive star reaches the end of its life, it doesn't fade quietly. It goes out in a blaze of glory so violent it can outshine entire galaxies. A supernova explosion is one of the most energetic events in the cosmos, unleashing in seconds the energy our sun will radiate over its entire 10 billion years. But these cataclysmic deaths aren't just spectacular light shows. They're cosmic recycling centers, scattering the star's guts across space in a fiery maelstrom of heavy elements. Iron from its core, oxygen from its outer layers, even gold and uranium forged in the explosion's unimaginable heat, all get hurled into the void at thousands of kilometers per second. This stardust doesn't disappear. It becomes the raw material for new stars, new planets, and ultimately, new life. The Crab Nebula is a stunning example of this process in action. In the year 1054, astronomers across Earth witnessed a star exploding so brightly it was visible in broad daylight for weeks. Today, we see the aftermath, a tangled web of gas and dust still expanding outward, carrying with it the elements that star created. But here's the twist. that debris isn't just dissipating. It's mingling with nearby molecular clouds, seeding them with the heavy elements needed to form rocky planets like Earth. Without supernovae enriching these clouds, the universe would be a very different place, filled with hydrogen-burning stars, but devoid of the carbon, nitrogen, and oxygen that make life possible. Supernovae don't just contribute ingredients, they also stir the pot. The shock waves from these explosions rip through surrounding gas clouds, compressing them in some regions and tearing them apart in others. It's like throwing a rock into a pond. The ripples can trigger collapses in distant pockets of gas, new rounds of star formation. Astronomers have spotted entire generations of stars whose birth was likely triggered by the death of a massive neighbor. The Eagle Nebula's famous pillars of creation, for instance, might owe their sculpted shapes to shockwaves from long-ago supernovae, their towering columns of gas squeezed just enough to ignite the next wave of stellar births. This feedback loop, stars living, dying, and birthing new stars, is what keeps the universe chemically alive. Each supernova adds another layer of complexity to the interstellar medium, enriching it with elements that weren't present in the early universe. The first stars, born from pure hydrogen and helium, couldn't form planets like ours. It took generations of stellar explosions to create the diversity of elements we see today. In a very real sense, the calcium in your bones, the silicon in Earth's rocks, and the iron in your blood all trace back to the death throes of ancient stars. Yet supernovae aren't the universe's only recycling agents. Even before they explode, massive stars shape their surroundings through fierce stellar winds and intense radiation. These forces carve out vast bubbles in the interstellar medium, pushing gas into dense shells where future stars might form. It's a reminder that stellar feedback isn't just about endings, it's about setting the stage for new beginnings. Every dying star is, in its own violent way, a midwife to the next generation. And as we piece together this grand cycle, we're not just studying distant astrophysics. We're uncovering the story of our own origins, written in the ashes of stars that died billions of years before our sun was born. The pillars of creation stand like ancient sentinels in the Eagle Nebula, their towering forms etched against the cosmos by the Space Telescope's iconic image. But these columns of gas and dust aren't just breathtaking scenery. They're a snapshot of stellar evolution in action. Each pillar stretches light years high, dense enough to shield pockets of gas from the scorching radiation of nearby stars while incubating new suns within their shadowy folds. Like cosmic sponges, they absorb the chaos around them, transforming it into something extraordinary, the seeds of future stars. Yet even these colossal structures aren't immortal. The very stars they birth will one day dismantle them. Young, massive stars nearby blast the pillars with ultraviolet light, slowly evaporating their outer layers in a process called. Jets from newborn protostars within the pillars themselves add to the erosion, carving delicate cavities like termites hollowing a tree. It's a paradox of creation and destruction. The pillars give life to stars, only for those stars to whittle away at their cradle. Current estimates suggest they may dissolve entirely within the next 100,000 years, a blink in cosmic time. But disappearance doesn't mean defeat. As the pillars erode, they expose the fledgling stars once hidden inside, releasing them into the galaxy like dandelion seeds on a stellar wind. These stars will carry chemical fingerprints of their birthplace, trace elements locked in the pillars, gas long before ignition. Future astronomers might one day identify these wanderers by their unique compositions, tracing them back to the Eagle Nebula like cosmic genealogy. What makes the pillars of creation so remarkable isn't just their fate, it's their role as a universal template. Similar structures pepper the cosmos, from the jagged spires of the Carina Nebula to the shadowy columns in NGC 6357. Each tells the same story: gravity's patience versus radiation's fury, a battle where both sides ultimately win. The pillars vanish, but the stars they forge endure, their light a legacy written across. This image froze them in time, but the James Space Telescope has since peered deeper, revealing heat signatures of protostars still forming within. Infrared eyes see through the dust, showing tendrils of gas swirling into newborn stars like rivers feeding a lake. These observations hint at an even richer narrative, one where the pillar's demise isn't an end, but a transition. The material they lose doesn't vanish. It joins the interstellar medium, ready to coalesce into new clouds, new pillars, new stellar nurseries. So when we gaze at the pillars of creation, we're witnessing a cycle as old as the universe itself. Structures rise, stars ignite, and the cosmic landscape shifts, but the ingredients remain, endlessly rearranged. The pillars remind us that destruction is just another form of creation, and every fading wisp of dust carries the promise of light yet to come. Dark matter is the universe's silent architect, an invisible hand shaping the cosmos without ever revealing itself. While we can trace the glow of gas clouds and the shimmer of newborn stars, dark matter leaves no light to follow. Yet its gravitational pull weaves through galaxies like an unseen scaffold, directing the flow of ordinary matter with ghostly precision. The question is whether dark matter exists. Its gravitational fingerprints are everywhere, but how deeply it influences the very birth of stars. Some theories paint dark matter as a cosmic choreographer, sculpting the distribution of gas long before gravity takes over. In this view, dark matter halos, those massive, invisible cocoons surrounding galaxies, act like gravitational molds, guiding gas into dense filaments where stars are more likely to ignite. Computer simulations show dark matter's tendrils stretching across the universe, creating a hidden skeleton upon which galaxies assemble. Without this unseen structure, the gas might scatter too thinly, leaving stars to form in isolated patches rather than the grand spirals and clusters we observe. But not all scientists are convinced dark matter plays such a direct role. Skeptics argue that once gas collapses into a cloud, local turbulence and magnetic fields take over, drowning out dark matter's subtler influence. They point to stellar nurseries like the Orion Nebula, where the frenetic dance of gas and radiation seems to drown out any whisper of dark matter's pull. If dark matter does shape star formation, its signal might be buried under the louder, more chaotic processes unfolding in these visible clouds. The debate hinges on a tantalizing clue: star formation rates in dwarf galaxies. These small, faint galaxies contain far more dark matter than ordinary matter, making them ideal laboratories. Strangely, many dwarf galaxies form stars at a sluggish pace, as if something is suppressing their stellar birth. One explanation: dark matter's gravity might be stirring up gas, preventing it from cooling and collapsing efficiently. It's like trying to light a candle in a windstorm. The flame struggles to catch. Yet in other corners of the cosmos, the opposite seems true. Some ultra-diffuse galaxies, nearly transparent yet rich in dark matter, blaze with unexpected stellar activity. Here, dark matter's grip might compress gas just enough to spark star formation where it otherwise wouldn't occur. This paradox suggests dark matter's role isn't just binary. It's a dynamic force that can both nurture and stifle, depending on the galactic environment. Unraveling this mystery could rewrite the story of galaxy evolution. If dark matter subtly nudges gas into fertile pockets, it might explain why star formation ebbs and flows across cosmic time. Or perhaps its influence is more like a backdrop, setting the stage but leaving the spotlight to visible matter. Either way, every newborn star we see might carry traces of dark matter's invisible touch, a reminder that the universe's grandest dramas often unfold in the shadows. The hunt for answers is pushing telescopes and simulations to their limits. Astronomers now map the faint gravitational distortions caused by dark matter, while physicists model how its particles might interact with gas on microscopic scales. Each discovery peels back another layer of the enigma, inching us closer to understanding how darkness and light collaborate to build the cosmos. One thing is certain, dark matter doesn't just lurk in the voids between stars. It might be the unseen architect of their birth, quietly shaping the universe's luminous tapestry from behind the curtain. Magnetic fields are the universe's invisible puppet masters, threading through stellar nurseries like cosmic marionette strings, guiding the chaotic dance of gas and dust without ever revealing their presence. Picture a dust cloud as a vast, turbulent sea, where gravity pulls material inward while magnetic fields crisscross through it like an intricate web. These fields might be imperceptible to our eyes, but their influence is undeniable. In some regions, they act like cosmic traffic cops, slowing down star formation by propping up gas against gravity's relentless pull. Elsewhere, they funnel material into narrow streams, accelerating collapse and igniting stars faster than gravity could manage alone. It's a cosmic tug-of-war where the rope is woven from pure magnetism. One of the most dramatic examples of this interplay unfolds in the Serpent's Cloud core, a stellar nursery where magnetic fields have sculpted gas into striking filamentary structures. Observations from radio telescopes reveal these fields aligning dust grains like tiny compass needles, creating channels where gas flows with eerie efficiency. Without this magnetic scaffolding, the cloud might collapse into stars haphazardly, like a building without a frame. But with it, the gas follows invisible road maps, streaming toward dense knots where protostars flicker to life. This isn't just a passive process. Magnetic fields actively shape the destiny of entire stellar generations. Yet these fields aren't always star-forming allies. In the Taurus molecular cloud, astronomers have spotted regions where magnetic pressure rivals gravity itself, putting star birth on hold. Gas here hovers in a precarious balance, too diffused to collapse but too constrained to disperse. It's as if the universe pressed pause, waiting for some external trigger, a passing shockwave or a stellar wind, to tip the scales. When that happens, the magnetic grip loosens, and gravity surges forward, transforming stagnant gas into stellar fire. This delicate equilibrium explains why some clouds seem to dawdle for millions of years before suddenly bursting with newborn stars. The real magic happens when magnetic fields and turbulence collide. Imagine a dust cloud as a stormy ocean, with waves of gas crashing in all directions. Magnetic fields don't just resist this chaos, they harness it. In simulations, tangled field lines can twist into helical coils, launching jets of material from protostars like cosmic catapults. These jets, some stretching light years into space, carry away excess energy and angular momentum, allowing the star to keep growing without spinning apart. Objects, those radiant stellar jets, are often the visible fingerprints of this magnetic choreography, proof that even in chaos, there's hidden order. What's truly fascinating is how magnetic fields scale up. They don't just shape individual stars, they weave through entire galaxies, influencing where and how stellar nurseries form. In spiral galaxies like the Milky Way, magnetic fields align with the arms, guiding gas into the dense regions where star formation thrives. Dwarf galaxies, with their weaker fields, tend to form stars more sporadically, as if missing a crucial ingredient. This galactic perspective suggests magnetism isn't just a local phenomenon. It's a universal architect, quietly shaping the stellar landscapes we see today. Unraveling these fields isn't easy. Unlike starlight, they don't emit or reflect photons. Instead, astronomers rely on subtle clues: the polarized light from dust grains, the faint radio emissions from molecules like carbon monoxide, even the way jets twist as they pierce through interstellar space. Each observation adds another piece to the puzzle, revealing how magnetism threads through the cosmos, stitching together the fabric of star birth. So the next time you gaze at a glowing nebula, remember, the real drama isn't just in the shimmering gas or the brilliant stars. It's in the invisible forces that sculpt them, the silent magnetic hands that mold chaos into light. Without these fields, the universe might be a very different place, darker, quieter, and far less alive. Cosmic winds are the universe's paradox, violent gusts that destroy even as they create. When a massive star ignites, it doesn't just shine, it screams. Furious streams of charged particles blast outward at millions of kilometers per hour, carving caverns in the surrounding dust cloud like a sandstorm eroding stone. The Orion Nebula's trapezium cluster offers a front-row seat to this phenomenon. Its young, hot stars have hollowed out a cavity over 12 light-years wide, their winds shoving gas aside so forcefully that new stars can't form in their immediate vicinity. It's nature's way of claiming territory, a stellar keep-out sign written in plasma and radiation. Yet these winds don't just clear space, they reshape it. As they collide with denser regions of the cloud, they act like cosmic snowplows, piling gas into compressed ridges and shells. The Rosette Nebula showcases this beautifully. What looks like a delicate floral structure is actually the aftermath of a stellar wind's bulldozing effect. The central star's outburst has swept surrounding material into a glowing ring, where the increased density is now sparking a fresh wave of star formation along its edges. Destruction and creation exist side by side, two sides of the same celestial coin. The key lies in the wind's intensity. Gentle breezes from smaller stars might merely ripple the surface of a molecular cloud, like a fingertip brushing water. But the gales from O-type stars, those blue-white giants dozens of times more massive than our sun, deliver hurricane-force impacts. Their winds carry enough energy to strip atmospheres from nearby disks or even tear fledgling stars apart before they've fully formed. The Carina Nebula's defiant finger is a stark reminder of this power, a pillar of gas stubbornly resisting erosion while its tip gets shredded into glowing streamers. What makes these winds truly fascinating is their ripple effect. When they slam into interstellar material, they don't just stop. They create shockwaves that propagate through the cloud. Like dominoes toppling in slow motion, these shocks can trigger collapses in regions far removed from the original wind source. Astronomers suspect this mechanism explains why some stellar nurseries, like NGC 6364, show star formation occurring in synchronized bursts across vast distances. One massive star's tantrum might set off a chain reaction that births an entire stellar generation. Yet for all their violence, cosmic winds follow surprisingly elegant rules. Their shape often reveals the magnetic fields threading through the cloud, like iron filings aligning around a magnet. In the Eagle Nebula, winds from newborn stars curve along invisible field lines, sculpting the famous pillars of creation into their eerie, finger-like forms. This interplay suggests that magnetic forces don't just resist the winds, they guide them, channeling their destructive power into patterns that ultimately foster new life. The legacy of these winds stretches beyond individual nebulae. When enough massive stars cluster together, their combined outflows can blow galactic-scale bubbles, structures like the local bubble surrounding our solar system, a cavity over 300 light-years wide carved by ancient supernovae and stellar winds. These bubbles reshape entire sections of the Milky Way, redistributing gas and metals in ways that influence star formation for millions of years. It's a reminder that the universe operates on interconnected scales, where the breath of newborn stars can alter the fate of galaxies. So the next time you see a glowing nebula's intricate filaments and cavities, remember, you're not just looking at static beauty. You're witnessing an ongoing conversation between wind and dust, chaos and order, endings and beginnings. These cosmic gusts are the universe's way of ensuring star birth isn't just a process. It's a story written one stellar breath at a time. Massive stars shouldn't exist, at least, not according to the same rules that govern their smaller siblings. For a star like our Sun, the process is straightforward. Gravity pulls gas into a dense core, heat builds, and fusion ignites. But for stars 10, 50, even 100 times more massive, the math breaks down. Their sheer luminosity creates a paradox. The moment they start shining, their radiation should blast away the surrounding gas, cutting off the fuel supply before they can reach such staggering sizes. Yet the universe is littered with these blue-white giants, burning bright and dying young. How do they defy their own physics? Astronomers have been wrestling with this puzzle for decades, and the answers might rewrite everything we know about stellar birth. One leading theory suggests massive stars form like smaller ones, just on cosmic fast-forward. Imagine a gas cloud collapsing not in millions of years, but in a frenzied 100,000. In this scenario, gravity works so quickly that the star gathers mass faster than its radiation can push material away. It's like trying to blow out a candle while someone pours gasoline onto the flame. The fire grows despite your efforts. Supercomputers simulating this competitive accretion show chaotic environments where multiple protostars vie for gas, with the biggest pulling in the most material before their own brilliance becomes a problem. The Tarantula Nebula, home to some of the most massive stars known, fits this model. Its dense, turbulent core is a feeding frenzy where only the fastest-growing stars survive. But there's a rival idea. Maybe massive stars aren't born from single collapses at all. Instead, they could be the product of stellar mergers, smaller stars colliding and combining like droplets of water. In crowded nurseries like the quintuplet cluster, where young stars orbit dangerously close, computer models show mergers might create behemoths that couldn't form solo. This would explain why the most massive stars often have bizarre companions or twisted orbits, as if something violent altered their youth. The debate gets even murkier when magnetic fields enter the picture. Some observations suggest these invisible forces might corral gas into dense streams, funneling material onto massive protostars despite their radiation. In the Orion molecular cloud, polarized light reveals magnetic channels that could act like cosmic pipelines, delivering fuel directly to growing stars while shielding it from their harsh glow. If true, magnetism isn't just a bystander, it's an accomplice, helping massive stars cheat their own limits. Then there's the disk accretion. Some astronomers argue that massive protostars, like their smaller counterparts, might gather material through swirling disks. These disks wouldn't just feed the star, they'd also shield the infalling gas from radiation, acting like a cosmic umbrella. The catch: no one's ever definitively spotted one around a truly massive protostar. The hunt is on, with telescopes like ALMA scouring nurseries for the telltale glow of these elusive structures. What's at stake isn't just academic, it's cosmic. Massive stars are the universe's alchemists, forging heavy elements in their cores and scattering them in supernova explosions. If we misunderstand their birth, we misunderstand the origins of everything from gold to oxygen. Their brief, brilliant lives shape galaxies, trigger new star formation, and even pave the way for life. Solving this puzzle isn't just about rewriting textbooks. It's about tracing our own atomic lineage back to these dazzling, defiant giants. The answer might lie in a combination of mechanisms, or something entirely unforeseen. Every new observation, whether of a hyperdense nebula or a bizarre binary system, adds another piece to the puzzle. One thing's certain: the universe has a flair for breaking its own rules, and massive stars are its most spectacular rebels. Interstellar dust might seem like the universe's afterthought, flecks of carbon and silicate smaller than a wavelength of light, drifting unnoticed through the void. But these microscopic grains are cosmic powerhouses, silently orchestrating the birth of stars with a precision that defies their size. Picture them as nature's nanoscale refrigerators. When gas in a stellar nursery begins collapsing under gravity, it heats up, and without a way to shed that energy, it would simply rebound like a squeezed spring. That's where dust steps in. Its jagged surfaces absorb heat and radiate it away as infrared light, cooling the gas just enough for gravity to keep pulling it inward. Without this cooling effect, star formation would grind to a halt, leaving galaxies filled with nothing but scattered, lukewarm gas. But dust's role doesn't end there. These tiny particles are also the universe's architects, laying the groundwork for planets. In the chaotic swirl of a disk, dust grains collide and stick together, forming pebbles, then boulders, and eventually the rocky cores of worlds like Earth. Some of these grains are even laced with ice, water, methane, and ammonia frozen into glittering mantles. When the young sun ignites, these ices vaporize, leaving behind a residue of organic molecules that could one day become the building blocks of life. The meteorite, a space rock that fell to Australia in 1969, contains stardust older than our solar system, studded with amino acids, proof that dust carries the raw ingredients of biology across the cosmos. What's truly astonishing is dust's diversity. Not all grains are created equal. Silicate dust, rich in silicon and oxygen, forms in the outer layers of aging stars and gets blown into space by stellar winds. Carbonaceous dust, often laced with polycyclic aromatic hydrocarbons, the same compounds found in soot, emerges from the smoky remnants of supernovae. These varieties behave differently. Silicates are excellent at radiating heat, while carbon grains excel at absorbing starlight. Together, they create a dynamic interplay that shapes how gas cools and collapses, influencing whether a cloud gives birth to a single star or a glittering cluster. The James Space Telescope has given us a front-row seat to this microscopic drama. Its infrared eyes detect the thermal glow of dust grains in nebulae like the Carina and Orion, revealing intricate structures where particles align along magnetic fields like iron filings. In some regions, dust forms delicate tendrils, woven into the fabric of the cloud. In others, it piles into dense knots, each a potential cradle for a future solar system. These observations hint at something profound. The universe's grandest structures, stars, planets, even life, owe their existence to the humblest of materials. So the next time you gaze at the dark lanes cutting through the Milky Way, remember, those aren't just empty voids. They're cosmic construction sites where dust weaves the tapestry of light. Without it, the night sky would be barren, no stars, no planets, no us. It's a reminder that even the smallest things can hold the universe together. The next decade of astronomy will rewrite the book on star formation, thanks to revolutionary telescopes designed to pierce the cosmic veil like never before. The James Space Telescope has already stunned us with its infrared vision, revealing protostars hidden in thick dust clouds, but it's just the opening act. Soon, ground-based giants like the extremely large telescope will join the hunt, with mirrors so vast they could spot a car headlight on the moon. Together, these instruments will act as time machines, capturing the universe's first stars flickering to life in the primordial darkness. What makes this new era so transformative isn't just sharper images. It's the ability to decode the chemistry of stellar nurseries light years away. Advanced spectrographs on these telescopes can identify individual molecules swirling around infant stars, from simple water vapor to complex organic compounds. Imagine tracing the entire of a planetary system, from its dusty beginnings to the moment it assembles the ingredients for life. The extremely large telescope's mid-infrared instrument, for example, will map the distribution of silica grains, the raw material for rocky planets, in disks with unprecedented detail. We might witness Earth-like worlds taking shape in real time, watching as gravity sculpts chaos into order. But the biggest revelations could come from the cosmic dark ages. Before galaxies filled the sky, the universe's first stars, population III stars, ignited in clouds of pure hydrogen and helium. These pioneers were likely monsters, hundreds of times more massive than our sun, living fast and dying in spectacular supernovae that seeded the cosmos with heavy elements. Until now, they've existed only in theory, but upcoming observations might finally catch their faint glow at the edge of observable time. The James Space Telescope is already scanning distant quasars for the chemical fingerprints these stars left behind, while future missions like the Laser Interferometer Space Antenna could detect gravitational waves from their cataclysmic collisions. Closer to home, these telescopes will solve lingering mysteries about our own galactic neighborhood. Why do some molecular clouds resist forming stars for eons, then suddenly burst into activity? How do magnetic fields shape the architecture of stellar nurseries? Even basic questions, like exactly how long it takes a star to grow from a gas knot to a shining sun, might finally get answers. The Nancy Grace Roman Space Telescope, set to launch in the late 2020s, will conduct wide-field surveys of star-forming regions, creating time-lapse maps of nebulae evolving over years. For the first time, we'll watch stellar birth as a dynamic process, not just isolated snapshots. Perhaps most thrilling is what we can't yet predict. Every leap in observational power has unveiled phenomena nobody imagined, from pulsars to exoplanets. As these new telescopes probe deeper into dust clouds, they might discover entirely new classes of celestial objects or reveal exotic physics governing star formation in extreme environments. One thing's certain, the universe has kept its deepest stellar secrets hidden in the shadows for billions of years. Now, at last, the lights are coming on. The story of planets begins in the same swirling chaos that births stars, those vast, dusty disks encircling newborn suns like cosmic pottery wheels. These disks are more than just stellar leftovers. They're dynamic construction sites where gravity, chemistry, and chance conspire to build worlds. Take the Space Telescope's iconic image of the disk around the young star HL. Its concentric rings and gaps aren't just artistic patterns. They're the fingerprints of planets carving their orbits, sweeping up dust and gas as they grow. This isn't some rare phenomenon. Nearly every young star we've observed hosts such a disk, suggesting planet formation isn't the exception, but the rule. What's astonishing is the sheer diversity of worlds these nurseries produce. In one corner of a disk, particles might clump into rocky pebbles, eventually snowballing into Earth-like planets. In another, gravity hoards hydrogen gas, crafting gas giants like Jupiter. The ingredients are surprisingly universal. Water, ice, silicates, and organic molecules mingle in these disks, but local conditions dictate the outcome. A hotter region near the star might bake away volatiles, leaving behind metal-rich worlds. Farther out, ices accumulate, creating the building blocks of ocean planets or icy dwarfs. The TRAPPIST-1 system, with its 7 Earth-sized worlds packed closer than Mercury's orbit, shows how wildly planetary architectures can vary even from the same basic recipe. The key to unlocking these mysteries lies in chemistry. ALMA, the Large Millimeter Array, has detected molecules like methyl cyanide and acetone in planet-forming disks, complex organics that hint at the raw materials for life. Some disks even contain a simple sugar, suggesting the universe might be prepping the ingredients for biology alongside the planets themselves. This doesn't just expand our search for habitable worlds, it rewrites the timeline for life's potential emergence. If these molecules are present at birth, they could be incorporated into forming planets, seeding them with life's precursors before their atmospheres even stabilize. Yet planet formation isn't a gentle process. It's a demolition derby where protoplanets collide, merge, and sometimes shatter. The early solar system likely witnessed such violence. The Moon's origin story involves a Mars-sized body slamming into young Earth, while Uranus's tilted axis hints at a cataclysmic knock. These chaotic events aren't bugs in the system, they're features. Without them, we might not have terrestrial planets with stable orbits or gas giants to deflect asteroids. The very chaos that seems destructive is what makes rocky, life-friendly worlds possible. The hunt for exoplanets has turned stellar nurseries into cosmic treasure maps. By studying disks like those in the Orion Nebula, astronomers can predict where and what kinds of planets might emerge. A disk with a thick ring of dust at the frost line, the distance where water freezes, might signal future icy moons like Europa. A gap carved by a young gas giant could indicate a system primed for smaller, inner planets. This predictive power is revolutionizing exoplanet searches, letting telescopes like James target stars most likely to host Earth analogs. But the real revelation: stellar nurseries aren't just making planets, they're making solar systems with personalities. Some disks, like those around massive stars, are tumultuous and short-lived, forging planets under extreme radiation. Others, around quieter red dwarfs, might simmer for billions of years, allowing complex chemistry to unfold slowly. The variety we see in exoplanets, from diamond worlds to evaporating giants, reflects this diversity of origin stories. Every planetary system carries the imprint of its nursery, a cosmic birth certificate written in orbital patterns and atmospheric compositions. So when we gaze at these dusty disks, we're not just seeing the birth of worlds. We're glimpsing the origins of potential life, the raw materials of future civilizations, and the answer to humanity's oldest question: are we alone? The universe seems to be whispering that planets, and perhaps life, aren't rare accidents, but an inevitable consequence of Stardust's endless dance. Star formation isn't a one-size-fits-all process. Some regions of space simmer with slow, steady stellar births, while others explode into frenzied bursts of activity like cosmic fireworks. The difference often comes down to a simple question: what's stirring the pot? In quiet corners of the universe, like the Taurus molecular cloud, gas collapses at a leisurely pace, forming solitary stars over millions of years. But in hot spots like the Tarantula Nebula, star birth erupts in violent spurts, with entire clusters igniting almost simultaneously. The secret behind these extremes lies in the triggers, external forces that act like a cosmic defibrillator, shocking dormant clouds into sudden life. Supernovae are one of the universe's most dramatic catalysts. When a massive star dies, it doesn't just vanish. It sends shockwaves rippling through nearby gas clouds at thousands of kilometers per second. These waves act like invisible fists, compressing the gas into dense pockets ripe for collapse. The Orion Nebula might owe its stellar boom to such an event, a long-ago supernova whose shockwave slammed into a quiet cloud, squeezing it just enough to ignite the trapezium cluster's brilliant stars. But supernovae aren't the only triggers. Galactic collisions, like the impending merger between the Milky Way and Andromeda, can also yank gas into furious motion, sparking starbursts so intense they outshine entire galaxies. Yet not all bursts need cataclysms. Sometimes the seeds of chaos are already embedded in the cloud itself. Turbulence, whether from passing stars, magnetic fields, or even the gravitational tug of spiral arms, can create pockets of instability where star formation snowballs. In the Carina Nebula, for instance, young massive stars bombard their surroundings with radiation, heating nearby gas until it expands and slams into cooler regions. This domino effect can trigger chain reactions, turning a quiet nebula into a stellar assembly line. It's like shaking a snow globe. The flakes might settle slowly on their own, but a sudden jolt sends them swirling in frantic patterns. The speed of star formation leaves lasting fingerprints on the resulting stellar populations. Slow and steady regions tend to produce smaller, longer-lived stars like our Sun, while starbursts favor massive, short-lived giants. This isn't just a curiosity, it shapes the evolution of entire galaxies. Starburst galaxies, like Messier 82, churn out stars so rapidly they exhaust their gas reserves in just a few 100 million years, leaving behind a glittering graveyard of aging stars. In contrast, galaxies with measured star formation, like the Milky Way, sustain their stellar nurseries for billions of years, fostering the stable environments where life-friendly planets can emerge. What's fascinating is how these patterns echo across cosmic time. The early universe was dominated by starbursts, frenzied, gas-rich environments where stars formed at breakneck speeds. But as galaxies aged and gas supplies dwindled, star formation slowed to today's more measured pace. This shift didn't just change the rhythm of the cosmos, it altered its chemistry. Those early, furious starbursts forged the first heavy elements, while later, steadier star formation distributed them into the diverse worlds we see today. The lesson, star formation isn't just about gravity and gas, it's a story of context. A cloud's fate hinges on where it is, what's around it, and whether the universe decides to give it a nudge. Some stars are born from patience, others from pandemonium, but both paths are essential to weaving the rich tapestry of the cosmos. Our sun didn't emerge from the void alone. It was born in a bustling stellar nursery, surrounded by thousands of sibling stars, all forged from the same primordial cloud of gas and dust. 4.6 billion years later, that cradle has vanished without a trace, scattered across the galaxy by stellar winds and gravitational tides. But the disappearance of our birth cloud isn't just a cosmic mystery. It's a detective story written in the chemistry of our solar system, the orbits of distant comets, and even the atoms in our bodies. The violence of the sun's infancy sealed its nursery's fate. As our star ignited, its newborn radiation and charged particle winds acted like a cosmic, blasting away the surrounding gas within just a few million years. Nearby massive stars, if our sun had any siblings that grew larger, would have accelerated this dispersal with their own ferocious ultraviolet radiation. Today, the remnants of that cloud are indistinguishable from the general interstellar medium, their molecules recycled into new generations of stars light years away. Yet subtle fingerprints remain, the precise ratios of isotopes in meteorites, time capsules from the solar system's birth, match no known region of our current galactic neighborhood, suggesting our sun's original cloud had a unique chemical signature now lost to time. Astronomers hunt for these dispersed siblings using stellar archaeology, mapping the motions and compositions of stars to find those that share our sun's DNA. Like tracing distant cousins through shared family traits, they've identified potential solar siblings in the HD 162-800 group and the Beehive cluster, all drifting apart at about 7 kilometers per second. If confirmed, these stars would be the last surviving witnesses to our solar system's chaotic infancy, their own planetary systems possibly carrying echoes of the same disk that birthed Earth. The most tantalizing clues might come from the solar system's frozen outskirts. The cloud, that vast shell of icy bodies surrounding us, could contain comets that formed alongside the planets but were flung outward before the birth cloud fully dispersed. Their chemistry might preserve uncontaminated samples of our original nursery's ingredients, a time capsule of pre-solar dust. Future missions to intercept these primordial icebergs could reveal what our corner of the galaxy tasted like before the sun began to shine. What's astonishing is how thoroughly a star can erase its origins. The same forces that give life, fusion's heat, radiation's push, also scour away the evidence of birth, leaving behind only planets as monuments. Our solar system's orderly architecture, from the rocky inner worlds to the gas giants, is the last visible trace of that vanished cloud structure, its density variations frozen into planetary orbits. Even Earth's water, once assumed to come solely from later comet impacts, may have been mostly present in the original disk, locked in dust grains that survived the sun's violent awakening. The lesson written in our missing nursery is universal. Stars are both creators and destroyers, weaving new worlds from old dust while erasing their own beginnings. Yet the cycle continues. The atoms that once formed our birth cloud now drift through other nebulae, some perhaps part of future solar systems. In that sense, the cloud never truly vanished. It simply became part of everything else, a reminder that in the cosmos, endings are just beginnings in disguise. Peering beyond the Milky Way, we find stellar nurseries that are both hauntingly familiar and utterly alien. The Whirlpool Galaxy, a mere 30 million light-years away, cradles dust clouds that mirror our own Orion Nebula, swirling filaments where gravity sculpts gas into new stars with the same patient precision. Yet in the Antennae Galaxies, where two spirals collide in a slow-motion cosmic train wreck, the rules change entirely. Here, galactic violence churns gas into frenzied knots, birthing super-star clusters so dense they outshine entire dwarf galaxies. This striking contrast reveals a fundamental truth. While the physics of star formation remains universal, the universe delights in rewriting the script based on location. Take starburst galaxies like Messier 82, where star formation rages at rates 10 times faster than in the Milky Way. These extreme environments turn dust clouds into stellar factories operating at breakneck speed, forging massive stars that live fast and die young. The recipe seems identical: gravity, gas, dust, but the conditions are amplified, as if the universe turned up the volume on star birth. Infrared observations reveal why. Galactic collisions or nearby quasars can flood these clouds with shockwaves, squeezing them into submission. The result? A fireworks display of star formation where a single cloud might birth thousands of stars in a million years, a blink compared to our neighborhood's more leisurely pace. Yet not all galactic nurseries follow this frenetic template. In small, metal-poor dwarf galaxies like the Large Cloud, dust clouds struggle to form stars at all. With fewer heavy elements to help gas cool and condense, these sparse nebulae produce stars reluctantly, their faint glow a far cry from the brilliance of Milky Way nurseries. Even more puzzling are the dark galaxies' ghostly clouds of gas detected through radio telescopes that somehow resist forming stars entirely. Some may be primordial relics, preserving conditions from the early universe before metals enabled efficient star birth. Others might be under the thrall of dark matter halos, whose peculiar gravity stifles rather than encourages collapse. The most dramatic outliers orbit supermassive black holes. At the heart of galaxy NGC 1976, a dust cloud spirals toward the central black hole, stretched into a glowing ring by tidal forces. Conventional wisdom says such extreme environments should tear clouds apart, yet here we see stars forming in the maelstrom, defiant sparks kindled in the shadow of annihilation. Meanwhile, in radio galaxy Centaurus A, jets from an active black hole blast nearby molecular clouds with enough energy to sterilize them. Yet pockets of star formation persist along the jet's edges. It's as if the universe insists on creating life even in the least hospitable corners. What emerges from these intergalactic comparisons isn't chaos, but a beautifully orchestrated diversity. The same laws of physics govern star formation everywhere, yet local conditions, the push of a quasar wind, the pull of a galactic merger, the whisper of ancient metal-poor gas, compose infinite variations on the theme. This cosmic flexibility ensures that while no two galaxies sculpt their stellar nurseries alike, each tells a part of the same grand story: how darkness gives way to light, and how the humblest ingredients, dust and gas, become the architects of cosmic evolution. Artificial intelligence is quietly transforming how we decode the universe's greatest mysteries, not by replacing astronomers, but by amplifying their vision. When the James Space Telescope beams back images of a stellar nursery, it's not just capturing light, it's delivering of data so vast no human team could process it in a lifetime. Enter AI algorithms, trained to spot the subtle patterns hidden in this cosmic deluge. A faint twist in a dust filament here, an almost imperceptible temperature gradient there. These are the fingerprints of star formation, clues that might take researchers years to notice, but that machine learning models can flag in seconds. One groundbreaking application is in mapping the intricate dance of gas and dust within nebulae. Traditional methods require painstaking manual analysis of spectral lines or radio emissions, but AI tools like neural networks can parse these signals at scale, reconstructing 3D models of star-forming regions with uncanny precision. For instance, in the Orion molecular cloud, algorithms have identified previously overlooked microcollapses, tiny pockets of gas on the verge of becoming stars, by detecting subtle asymmetries in millimeter-wave data. It's like giving astronomers infrared goggles to see through the cosmic static. These systems aren't just passive observers, they're active predictors. By training on thousands of known star-forming regions, AI can simulate how a given cloud might evolve under different conditions. A team at the University of California recently used this approach to forecast bursts of star formation in the Carina Nebula months before telescopes spotted the actual stellar ignition. The model didn't just rely on gravity and gas density. It factored in magnetic fields, turbulence, even radiation pressure from nearby stars, variables so complex they'd overwhelm conventional simulations. Perhaps the most surprising AI contribution is in solving the missing pieces puzzle of galactic evolution. When astronomers compare young galaxies to mature ones, there's a mismatch in star formation rates. The early universe seems to have produced stars too efficiently. Machine learning helped crack this by analyzing faint, distorted galaxies in steep field images, revealing that mergers and gas inflows created short-lived starbursts modern telescopes had overlooked. The AI essentially connected cosmic dots humans didn't even realize were related. Yet these tools aren't infallible. An algorithm trained on Milky Way-like galaxies might misinterpret the chaotic nurseries of distant starburst galaxies, where different physics dominates. That's why the best systems now use hybrid approaches, combining AI's pattern recognition with astrophysicists' theoretical frameworks. The result? A collaborative dance where machines highlight anomalies and humans interpret their meaning, each pushing the other toward discoveries neither could achieve alone. The future shines even brighter. Upcoming projects like the Observatory will generate terabytes of data nightly, a volume unthinkable without AI assistance. Already, prototype systems are learning to identify rare objects, like the elusive first-generation population III stars, by their unique chemical signatures in simulated data. Others are designing optimized telescope observation schedules in real time, ensuring precious instrument time isn't wasted on empty patches of sky. What's truly revolutionary isn't the technology itself, but how it's reshaping the questions we can ask. Instead of just where a star is forming, we can now explore why here and not there, or what primordial ripple set this chain of star birth in motion. AI isn't taking the wonder out of astronomy. It's revealing layers of complexity we never knew existed, turning every cosmic nursery into a living puzzle waiting to be solved. Imagine a future where humanity doesn't just observe the cosmos, we shape it. The idea of tinkering with star formation might sound like science fiction, but the seeds of this possibility are already sprouting in labs and theoretical papers. Advanced civilizations could one day harness the power of magnetic fields, lasers, or even dark matter to nudge molecular clouds into collapsing, or prevent them from doing so. The implications are staggering. We might ignite stars in barren regions of space to create new habitats or suppress stellar births to conserve galactic resources. But with such power comes a responsibility heavier than a neutron star. The ethical dilemmas lurking in these scenarios force us to confront a question humanity has never faced before. Do we have the right to play cosmic architect? The risks of meddling with star formation aren't just hypothetical, they're potentially cataclysmic. A miscalculation in manipulating a massive molecular cloud could trigger runaway gravitational collapse, birthing a star so unstable it detonates as a supernova prematurely. The blast wave from such an event could sterilize nearby star systems, wiping out extraterrestrial life we didn't even know existed. Even subtler interventions, like scattering dust grains to cool a cloud faster, might unintentionally alter the chemical makeup of future planets, robbing them of the organic molecules needed for life. The universe has spent billions of years refining its star-forging recipes. Our clumsy attempts to improve them could have consequences echoing across. Yet the allure of intervention is hard to dismiss. In a galaxy where habitable worlds might be rare, guiding star formation could be the ultimate act of cosmic stewardship. Picture a distant cloud rich in heavy elements but stalled in its collapse. A gentle nudge from artificial magnetic fields might the birth of a solar system perfect for life. Or consider civilizations facing energy shortages. Harvesting the raw materials of a disk could provide resources for trillions. The moral argument here mirrors debates about terraforming Mars or climate engineering on Earth, but scaled up to galactic proportions. If we can prevent a nebula from forming deadly massive stars, whose supernovae would sterilize entire regions, don't we have an obligation to act? The ethical framework for such decisions doesn't exist yet, and philosophers are starting to sketch its outlines. One principle gaining traction is the Cosmic Prime Directive, the idea that natural processes should remain undisturbed unless intervention prevents greater harm. But defining harm in a universe where life might take forms beyond our imagination is fraught with uncertainty. Would suppressing a supernova to protect one civilization unintentionally deprive another of the heavy elements it needs to arise? The chain reactions of stellar engineering could ripple across space and time in ways no simulation could predict. Even if the technology matures, the political and cultural challenges might prove insurmountable. Who gets to decide which stars are born and which are? Would galactic zoning laws emerge, with some civilizations designating protected wilderness nebulae, while others industrialize star formation for energy? And how would we handle the discovery of another intelligent species already manipulating the same clouds? Would it lead to collaboration or cosmic conflict? History suggests that control over resources rarely leads to peaceful outcomes, and stars are the ultimate resource. Perhaps the most humbling thought is this: star formation isn't just a mechanical process. It's the universe's way of recycling itself, turning the ashes of dead stars into new possibilities. Every atom in our bodies was forged in these cosmic furnaces, and every planet's existence hinges on the delicate balance of forces within stellar nurseries. To intervene is to risk breaking a chain of events that has, against all odds, led to us. The stars have always been beyond human reach, not just physically but ethically. As we stand on the brink of potentially rewriting cosmic history, we must ask not only whether we can, but whether we should. The answer might define not just our future, but the future of the galaxy itself. Black holes aren't just cosmic vacuum cleaners, they're master sculptors, shaping the destiny of entire galaxies with their paradoxical influence. At the heart of nearly every large galaxy, a supermassive black hole lurks, weighing millions to billions of times more than our sun. These behemoths should be the ultimate star killers, blasting their surroundings with enough radiation to strip gas clouds apart before stars can form. Yet the universe loves a good plot twist. In some galaxies, these same black holes act like cosmic, triggering waves of star birth with shock waves that ripple through interstellar space. The difference between destruction and creation often comes down to a delicate balance. a dance of power where timing and distance mean everything. Take the Phoenix Cluster, a galaxy group over 5 billion light-years away. Here, the central black hole pumps out jets of energy so intense they carve enormous cavities in the surrounding hot gas. But along the edges of these cavities, something remarkable happens. The displaced gas piles up like snow in front of a plow, compressing into dense shells where gravity can finally take over. The result: a stunning ring of newborn stars glowing blue against the blackness, a stellar nursery forged in the aftermath of destruction. It's as if the black hole cleared a space and then handed the universe a fresh canvas. Not all galaxies get such a happy ending. In Quasars, galaxies with hyperactive black holes, the story turns apocalyptic. These monsters devour material so voraciously that their radiation outshines every star in their host galaxy combined. The energy floods nearby molecular clouds, heating them until they can't collapse. Star formation doesn't just slow, it shuts down entirely, leaving behind a red and dead galaxy where no new stars ignite. The black hole effectively sterilizes its own home, a cosmic case of self-sabotage. The key to this duality lies in the black hole's feeding habits. When material falls in smoothly, it tends to produce steady radiation that stifles star birth. But when the inflow is chaotic, clumpy, and irregular, it generates shock waves that can compress gas instead of vaporizing it. Astronomers have spotted this in Messier 87, where the famous jet from its central black hole interacts with surrounding clouds, creating pockets of star formation even as it blasts other regions barren. It's a reminder that black holes aren't monolithic destroyers. They're dynamic forces, capable of both chaos and creation. This push and pull has shaped galactic evolution since the beginning. In the early universe, quasars likely played a brutal but necessary role, quenching star formation in some galaxies to prevent them from growing too large too fast. Without this suppression, galaxies might have burned through their gas supplies prematurely, leaving the modern universe devoid of star-forming fuel. Meanwhile, in quieter epochs, black hole feedback, those shock waves and jets, may have helped regulate star formation, ensuring galaxies didn't form all their stars at once. Like a cosmic thermostat, black holes help maintain balance, even if their methods seem violent. The legacy of this interplay is written in the stars themselves. Some astronomers suspect our own Milky Way's central black hole, Sagittarius A, has gone through cycles of feeding and fasting, alternately stifling and sparking star birth in the galactic center. The young stars orbiting perilously close to it, stars that shouldn't exist given the harsh environment, might be survivors of one such turbulent epoch. Their presence hints that even in the most hostile territories, star formation finds a way. Understanding this duality isn't just academic, it's key to solving one of astronomy's biggest mysteries: why some galaxies teem with young stars while others fade into quiet old age. Black holes might be the missing link, the invisible hands guiding galaxies along different evolutionary paths. As telescopes like the James Space Telescope peer deeper into galactic cores, they're revealing more of these intricate relationships, showing us that destruction and creation in the cosmos aren't opposites, they're partners in an endless dance. The universe's first stars weren't just different, they were alien. Born from clouds of pure hydrogen and helium, untouched by the heavier elements that fill modern nebulae, these pioneers, dubbed population III stars, burned hotter, died younger, and left behind a legacy we're only beginning to decode. Unlike today's stars, which form in dust-rich nurseries, these primordial giants had no dust to help cool their birth clouds, no carbon or oxygen to forge complex molecules. Their formation was a stripped-down cosmic ballet, gravity working with nothing but the simplest ingredients. Yet despite their fleeting existence, their fingerprints might still linger in the most unexpected places, hidden within ancient dust clouds that drifted through the cosmos for over 13 billion years. The hunt for these ghosts begins with their unique chemistry. When the first stars exploded as supernovae, they spewed their nuclear-forged elements into the void, seeding the universe with its first heavy metals. But crucially, the earliest supernovae were unlike anything we see today. Without elements like carbon or oxygen to act as cooling agents, these stars likely collapsed directly into black holes or exploded with such violence they scattered their material like cosmic shrapnel. These parent stability, supernovae would have left behind a distinct chemical signature, an overabundance of odd-numbered elements like phosphorus and sodium, and a curious absence of others. Remarkably, astronomers have spotted this exact pattern in some of the universe's oldest known stars, like the faint red dwarf He 1327. These ancient survivors found in the Milky Way's halo might be second-generation stars, children of those first vanished giants. But the real smoking gun could lie in dust itself. In 2023, the James Space Telescope detected tiny graphite and silicate grains in a galaxy just 700 million years after the Big Bang, far too early for ordinary stars to have produced them. One theory: these grains are the shattered remains of population III stars, their supernovae so powerful they vaporize the star's cores into microscopic particles. If confirmed, this discovery would rewrite the timeline of cosmic evolution, proving that dust, and by extension, the building blocks of planets, existed almost as soon as stars themselves. The search isn't just about nostalgia for the universe's infancy. These first stars set the stage for everything that followed. Their explosions determined how quickly galaxies could form, how efficiently gas could cool, even how life's ingredients were distributed. Some models suggest they were monstrous, hundreds of times the mass of our sun, burning so bright their ultraviolet radiation ripped apart nearby gas clouds, delaying subsequent star formation. Others propose they formed in tight clusters, their combined gravity sculpting the first proto-galaxies. Without understanding them, we're missing the first chapter of cosmic history. Yet for all their importance, population III stars remain frustratingly elusive. Their light, stretched and dimmed by the expanding universe, is too faint for even our best telescopes, unless we get lucky. Gravitational lensing, where massive galaxy clusters bend light like a magnifying glass, might one day amplify a telltale glimmer from the cosmic dawn. Until then, we're left with echoes, the odd chemistry of ancient stars, the whispers of primordial dust, and the growing realization that the universe's darkest shadows might still hide its very first light. From the darkness of dust clouds comes the light of stars, each one a testament to the universe's endless creativity. We've wandered through stellar nurseries where gravity and chaos collide, watched protostars fight for survival against magnetic fields and radiation, and traced the atoms in our bodies back to the heart of dying giants. These cosmic cradles are more than just star factories. They're time machines, revealing how the universe transforms simplicity into complexity, darkness into brilliance. Consider this: every star begins as an impossibility. A cloud of gas, so diffuse you could fly a spaceship through it without noticing, defies the odds to collapse into a glowing sphere. The same forces that tear things apart, turbulence, magnetic fields, stellar winds, somehow conspire to build instead of destroy. It's as if the universe operates on a hidden principle. From chaos comes order, from scattering comes unity. The pillars of creation, objects, brown dwarfs, each is a chapter in this grand story, showing us that creation isn't always gentle, but it's always relentless. Yet the most astonishing part isn't how stars form, it's how their birth shapes everything else. Without stellar nurseries, there would be no planets, no chemistry, no ingredients for life. Those microscopic dust grains we once overlooked turn out to be the universe's master builders, crafting everything from asteroids to oceans. And the explosions that end massive stars, They're not just finales, they're encores, scattering stardust for the next generation. This cycle, repeated across billions of years, has filled the cosmos with the very elements that let us exist. The journey doesn't end here. With every breakthrough, every infrared image from James, every simulation of ancient supernovae, we peel back another layer of the mystery. What triggers star formation in some clouds but not others? How do magnetic fields sculpt galaxies we've never seen? The questions multiply, but so do the tools to answer them. Telescopes now under construction will probe deeper into dust-shrouded nurseries, while AI sifts through data for patterns no human could spot. The universe isn't done surprising us. So when you step outside tonight and gaze up, remember, you're not just looking at stars. You're seeing the aftermath of cosmic battles, the triumphs of gravity over chaos, the echoes of explosions that happened before Earth existed. Those flickering lights are more than distant suns. They're proof that even in the coldest, darkest corners of space, the universe finds a way to shine. And if this exploration has sparked your curiosity, there's so much more to discover. The cosmos is vast, but every mystery we unravel brings us closer to understanding our place in it. The stars are waiting. Let's keep searching.